Let's take a look at how calculus helps us analyze some of these things. So let's define a couple of variables. So x is our position function, v is our velocity function, a is our acceleration. Again, all of these things describe an object's motion, right? An object's motion is based on where it's located, how fast it's changing its location, right? That's velocity, that's in meters per second. And then its acceleration, which is in meters per second squared, or probably better to think of it as meters per second. So for example, if we take a look at if something had a velocity of 4 meters per second, we would be saying that it is increasing its position, right? This is a positive velocity. Velocity is a vector. It's increasing its position by 4 meters every second. So the velocity is the rate at which we're changing position. Velocity is the rate at which we're changing position. Right? This is the calculus version. And this dx dt, that's how you'd say that, dx dt, you could write it as this. This is the time derivative of position. The rate at which you're changing your position is velocity, and some people even call it x prime. All of those things mean the exact same thing. The velocity is how fast you're changing your position. Just look at what a velocity is. It's in meters per second. Now if we look at an acceleration, what would an acceleration of, let's say, 3 meters per second squared be? Well, an acceleration is the rate at which you're changing your velocity. So the acceleration then is dv dt, meaning the derivative of velocity. You could say it's the time derivative of velocity, which you could call it as v prime, and actually you can call it as x double prime. The second derivative of position is acceleration. Again, look what this means. An acceleration of 3 would be an increase of your velocity by 3 meters per second every second. And again, all of these things, this is just notation, but this is the calculus. This ddt is an operator. It's like saying multiply by something or divide by something. And you are taking the time derivative of position. And again, we define velocity as that. It's the rate at which we change our position, whereas acceleration is the rate at which we change our velocity. Velocity and acceleration are both vectors, meaning the negative sign or a positive sign is associated with the direction. A negative velocity is moving left, a positive velocity is moving right. A positive acceleration is an increase of velocity, a negative acceleration is a decrease of velocity. We'll have to talk about speed later in terms of looking at a bunch of examples, but the speed is the magnitude of the velocity vector. And so if you're going really fast to the right or really fast to the left, your speed is the same. It doesn't care about what direction you're going. It just talks about the magnitude, right? Whether it's a negative 40 or a 40, the speed, of course, is just 40 meters per second. Okay, let's just do a couple examples of the calculus. The first way is using the power rule. So I'm going to teach you how to actually take a derivative. And so let's just start out with x. Let's say x is 12 t squared minus 10t plus 5. And we can talk about all of these things. Okay? We can look at what all of these things actually even represent. If you look at what is x of 0, well, that's your position at t equals 0. If you plug in 0 here, you're just going to get the 5. And so hopefully you can tell that the 5 is just our initial position. Okay? Now I want to find the velocity. Now I need the power rule. The power rule says decrease the power by 1, or excuse me, bring the power down, decrease the power by 1. So this is a power 2, bring the 2 down, which will make that 24, and then decrease the power by 1, which makes it a t. Now this is t to the first. Bring that power down, decrease the power by 1. Well, making a t to the 0 power is just 1, so you just get negative 10. And then there is no power, but if you brought, or there is a 0 power. If you bring the 0 down, it's going to go away. right? The derivative of a constant is 0. Just think about, what does the derivative mean? When you think derivative, besides thinking about the rate of change, the derivative is an equation for the slope, right? The graph, the rate of change is the slope. Well, what is the slope of just a 5? Well, a 5 would be a horizontal line, and you'd get back this. Okay, both of these make sense. What's the slope of 10t? Well, it's just 10, right? If you graph this, this would be just a line, and you would get this. And we take another derivative to find acceleration, and we would just get 24, right? Bring the power down, decrease the power by 1 makes the t go away, and then here. Okay, so that's a nice, easy example of if I gave you a position function, you could find the velocity and acceleration. And again, these are velocities and accelerations that are functions of time. They're not average velocities, they're instantaneous velocities, because I can actually now say, what is the velocity at exactly 1 second? Well, I'm just plugging in 1 to here, and I get 14. What's the acceleration at 4 seconds? Well, it turns out this is constant acceleration. So it happens to always be 24. Okay, and so we would get that for that rule. We can do any sorts of rule, but right now we're just looking at polynomials. Eventually, when you get to more calculus, you will learn other things. But I could get something like 4t cubed minus 8t squared plus 4t minus 10. And I would take a derivative. Right? The derivative is asking for an equation for the slope. It's looking for the rate of change. Remember, the slope of an x graph is going to be velocity. And it just happens that the slope is changing. Well, because the velocity is a function of time. It's not the same velocity every time. Bring the power down. Decrease the power by 1. Bring the power down. Decrease by 1. Bring the power down. In this case, the power is just 1. Decrease the power by 1. Derivative of a constant is 0. So I get a velocity equation. Acceleration. Take a derivative of velocity. Bring the power down. So it's 24. Decrease the power by 1. Bring the power down. And we get that. And so if you think about it, look what happens here. Quadratic, linear, constant. Cubic, quadratic, linear. Is that relationship always true? Well, of course it is for polynomials. You're always decreasing the power by 1. So a cubic goes to a quadratic, it goes to a linear. And so if you think of some of our standard equations, they're all quadratics. Well, that's because they're constant acceleration problems. If you're having a problem where it's constant acceleration, you're going to get a linear velocity, and you're going to have a quadratic position. If you have a cubic position function, you're going to get a quadratic velocity and a linear acceleration, right? Second order, first order. And again, we could do all sorts of things with this. We could figure out when the acceleration is positive, when it's negative. We could figure out when the velocity is positive, when the velocity is 0, when the velocity is negative. That's all about it changing direction, moving to the right, moving to the left. I can figure out where this thing is located at any time by just plugging in x. But there's a definite connection, and again, all of this uses calculus. And for right now, the only thing you have to be able to understand is the power rule. The power rule for derivatives is bring the power down, decrease the power by 1. Okay? And in these two examples, I gave you the position and asked for the acceleration. We are going to have to go the other direction. Okay? So the calculus now changes, and we will look at the other direction of this. Okay, I'm going to remind you of what we just learned. We just learned that we have position, and if we look at the derivative of position, the rate at which we're changing our position is the velocity. Our acceleration is the rate at which we're changing velocity. Okay, and that's all about looking at slopes. Okay, so the calculus, the first part about calculus, is all about looking at the slopes of those things. All right, now I want to look at the accumulation. Okay, and that's basically the whole second part of calculus. The accumulation says this: what if I knew I was going a velocity of 10 meters per second for 5 seconds? How far do I want to go? Well, if I accumulate this velocity for 5 seconds, I go, of course, 50 meters. Right? That's a really easy question. From a graph, it would look like this if I plotted velocity versus time. Well, if the velocity was just constant, 4 or 5 seconds, the area under that curve would be 50 meters. Well, think about it. For the first second, second second, third second, fourth second. Well, how far did I go in that first second? Well, I was going 10 meters per second. For 1 second, I would have went 10 meters. And so each one of those is 10. Accumulating velocity over time is 50. And the way we would do that algebraically, it's really the change in your position. Delta x is the integral, okay? Integral. When you think integral, you want to think it's an accumulator function. It's a summing function. If you sum up all of your velocities, the accumulation of velocity over time, which is going to be this dt, and again, you'll get in much more depth of this later on, but the accumulation of velocity over time is your change in your position. This is really easy. Go 10 meters per second for 5 seconds, you went 50 meters. Okay? So the integral of 10 dt from 0 to 5. I know that's a lot. This is a lot I'm asking you for, and eventually you'll take a ton of time to do it in calculus, but we're just going to kind of get you started here. This symbol is the integral symbol. It's an accumulator. It's summing up these velocities, which happen to be a constant, over time, and you're going to let time vary from 0 to 5 seconds. And here, this is the reverse power rule, or the power rule for antiderivatives. Okay? You're going to increase the power by 1, and then you're going to divide by the new power. You're going to do the exact opposite. Okay? So for instance, if I had a velocity of 4t, how do I get the position? I increase the power by 1 and divide by the new power. So it'd be 2t squared. Increasing the power by 1 makes it from t to the first to t to the second, and then dividing by 2 changes the 4 to a 2. And just look, what if you followed our old derivative rules? What if I had this and I would go backwards? Bring the power down, decrease the power by 1. See how they're completely related? The only change in here is you have to add some c value. And the c value you're going to have to find using some initial value. Remember up here, I said the accumulation of velocity over time is your change in your position. Right? This represents the delta x. Where you're located, your position, depends on some starting value. Because what if I knew, given this, what if I knew that at 0, you were located at a position of 5? What would c be? Well, that means when you plug in 0 for t, you have to get a position of 5, which means c must be 5. You see how I use this and this together to get the actual position function, right? We call this an initial value. If you're actually doing an integral and looking at the times, well, in this case, we would do the integral, follow the rule, increase the power by 1, divide by the new power, and you get 10t. The integral of 10 is 10t, just like the derivative of 10t is 10. And then we're going to put this vertical line, and we're going to evaluate that from 0 to 5, which means you're going to plug in 5 and subtract plugging in 0. So this is just 50 minus 0, and you get 50 meters, just like we said over here. Right? The accumulation of this velocity is 50 meters. Now, where are we located? I don't know. Wherever we started, plus 50. This 50 is the rate of that change. What happens if the accumulation isn't constant? We can't make these nice boxes. Well, that's what we did down here. Think about down here. This velocity function is some 4t. It's some function, which makes summing up these boxes more difficult, but that's why we have calculus rules. Let's say I was going this velocity and I was going, oh, I don't know, for 10 seconds. If I want to find out how far I went from 0 to 10 seconds going a velocity of 4t, I just accumulate that velocity over that time period. The integral of 4t is 2t squared. and then evaluate it from 0 to 10. Again, plugging in 10 gives me 200, plugging in 0 gives me nothing, and that gives 200 meters. And that's my delta x. If I want to know where I'm actually located, well, then I'm at 205, because I started at 5 and I went 200, now I'm at 205. So like x of 10 would be 205. Again, there's two real major fundamental parts of how we use calculus. One is looking at the rate of change of things, right? We're looking at the derivative. The derivative is what we call, right, we would say the derivative of dx dt and dv dt is how we find velocity and acceleration given a position function. Use the power rule, bring the power down, decrease the power by 1. And so if I give you any position function, eventually the position might be an exponential, or it might be a cosine or a sine curve. In simple harmonic motion, it's going to oscillate back and forth, back and forth. Your position might be a quadratic, which gives a linear velocity and a constant acceleration. And then the other case is the case we just got done doing, and that's looking at the accumulation of things. That's where I give you a velocity and I ask you, well, how does that affect the change in position? Or I could give you an acceleration. I could give you an acceleration of 2t. You could use calculus to find the velocity as a function of time, which would just be t squared plus some c value, and you'd have to tell me the initial velocity in order to find the actual velocity function. But again, we can accumulate acceleration to get velocity. We can accumulate velocity to find the position on a graph, right? So what we're saying here is if I have x of t and I look at the slope here, let's look at the slope here, okay? Anytime the slope here is velocity. Well, what happens if it's a changing slope? Well, then that's an acceleration, right? The rate at which the slope is changing is the rate at which the velocity is changing, which is how we have defined acceleration. Here, the velocity is always positive. You see how over time my position is always increasing? But it's not always increasing at an increasing rate. Here, this is acceleration, positive acceleration, and here's negative acceleration. See how my velocity is increasing, bigger and bigger and bigger slope? Now my slope's getting smaller and smaller and smaller, right? This would be speeding up, and this would be slowing down. See how the slope here is 0? No change in position, no velocity. I could look at a velocity curve. And this could be some velocity curve. Well, the slope here is acceleration. This is negative acceleration, positive acceleration. This is a velocity of 0, which means, oh, I must have changed direction here. This is a positive velocity, and then this is a negative velocity. So that's a turnaround point, moving to the right, moving to left. The accumulation of the velocity, meaning adding up the area there, well, that's how far I went to the right. This blue, all of this corresponds to a negative velocity. So that's how far I went to the left, and then it looks like I turned around again, and I started going back to the right. And so we can look at the slopes, and we can look at the accumulations. I could look at an acceleration graph. If I looked at an acceleration graph, maybe the acceleration looked like that. This is me always having a positive acceleration. See how acceleration is always above the x-axis? And the accumulation of that acceleration would be how much I increased my velocity by. Increased because this is a positive area. If the acceleration was negative, then it would have been a decrease. And so we connect those things. Again, when you see a symbol like this, dx dt, that's talking about the velocity. dv dt, the derivative of velocity, is acceleration. And the total flip side of that, they go hand in hand. The change in the position is the accumulation of velocity over time, where the change in velocity only happens when you accumulate acceleration over time. I mean, just think about what those words mean. If you accelerate for a certain amount of time, you've increased or decreased your velocity. If you're traveling a velocity for a certain amount of time, you've increased or decreased your position. I mean, these things go hand in hand. This is all about slopes and derivatives. This is about integrals, or sometimes they even call them antiderivatives, and it's about the accumulation of things. Okay, one is about burning calories per second, and one is about how many calories you've burned over the 10 seconds of your workout, or whatever. But again, one is talking about slope, and one is talking about area. And these calculus concepts will continue to happen. We'll look at the rate at which you change your momentum versus time. Well, that'll be a force. The accumulation of force over distance will end up being the work done on an object. So these concepts will continue to build and build, but in kinematics, we pretty much use graphs to look at slopes and areas, and then we use the notation of the derivative and the antiderivative or integral to find the accumulation of things over time. And really, right now, all you have to know is the power rule. The power rule is very similar. Again, for derivatives, you bring the power down, decrease the power by 1, and the other one you increase the power by 1 and divide by the new power. I mean, hopefully you can imagine that they're doing the complete opposite, right? If I have position is 6t squared, if I take a derivative to get velocity, I would get 12t. Bring the power down, decrease the power by 1. If I have a velocity of 12t and I increase the power by 1, making it t squared, and divide by the new power, 12 divided by 2 is 6. Again, they're completely hand in hand with each other. Hopefully this was a good review. I know we've talked about it in class, and hopefully you can watch some other videos if not, but of how calculus plays a role in the early onset, the kind of analysis of kinematics. Kinematics being the study of an object's motion, typically using position, velocity, and acceleration.